In previous recording, we studied what is concurrent program. The concurrent program is the program which is written to create the illusion of simultaneity by allowing multiple threads run the different section of code. One of the key challenges when you write the concurrent program is the race condition. What is a race condition? This race condition is defined as the problem of inconsistency when more than one thread tries to update the shared common variable. In order to guard against prevent this race condition in concurrent program, we need one of the most important primitive that implement the mutual exclusion. We studied several ways to implement this mutual exclusion as one primitive, which is lock and unlock, and some shared variable and unlock. So basically, we spent few hours to talk about how to implement this lock and unlock. And what is the user code? This section of code guard by this lock and unlock is known as a critical section. Once we correctly implement this lock and unlock, whichever thread to grab this lock can enter this critical section and execute this critical section as one logical entirety, which is known as logical atomicity. Now, this is the way we achieve the correct synchronization amongst competing threads in concurrent program. In this lecture, I would like to introduce another important primitive, which is quite useful primitive in addition to this lock and unlock, which is known as condition variable. This is quite fun and important lecture. So let's study another concurrent program primitive, which is known as the operation on the condition variable. Let me begin with what is condition variable. Condition variable is a specialized data structure, which is explicit linked list, which is explicit queue. What is this queue for? This queue is a linked list of the threads and which waiting on some special condition. You may wonder, then what is this condition? This condition is programmer defined. Whoever writes concurrent program can define what is the condition for this explicit queue. And there's, in addition to this explicit queue, there's one important API, which is a signaling. This signaling means when a particular thread to make certain condition be satisfied, and that thread can notify this condition variable, which is known as signaling. When this condition variable being notified, one of the thread waiting on this explicit queue will be dequeued and moved to the ready list for the CPU. If there is no thread waiting on this explicit queue, then the signaling turns out to be simple no-op operation. Then why we need these condition variables as one additional concurrency primitive other than the lock and unlock? Let's take a look. Very simple program. This is multi-threaded program. The parent thread printing parent. And then it creates the child thread, which is executing this child subroutine. What does the child subroutine do? It prints the child. After creating the child thread, what does the parent thread does? It prints the parent end. I forgot to put begin. When you actually code this simple program and compile it, run, and this will be the output. Can you guarantee when you run this program more than one times, can you guarantee this is the output comes out every time? Well, you cannot guarantee that. This is the common case, but when you write the concurrent program, there might be some race. What I meant by race is this may not be the order that you expect. There might be some surprise when you run millions of times, once or twice, when you run millions of times. Depending on the workload of your system, the output might be different. Maybe parent begin will be printed first, and after creating the child thread, then the parent thread continue to run. Therefore, this child may be printed after the parent thread printing the parent end. The question is, if you would like to have this output every time you run this particular program, to guarantee this order of the output, what changes that you need to make to this simple program? The easiest fix is introduce one shared variable, which is a done. And then after the parent thread create this child thread, because it has no idea who will run first after the creation of this thread, parent thread or child thread. Therefore, we use, and this thread use this done variable for the synchronization. While done is equal to 0, then the parent thread will busy wait. What's the busy wait? Until it's just wasting the CPU cycle until this condition done is set to true. By doing this way, regardless of the scheduler, whether the parent thread will be scheduled first or child thread scheduled first, and we can achieve the desired synchronization. Let's say, after the creation of the child thread, see, if the child thread scheduled first, and print the child and set the done flag as 1, therefore, the expected order comes out. What if the scheduler scheduled the parent thread first? Let's see what happens. After the creating the child thread, parent thread continue to execute, but the done flag is still 0, therefore it will spin on this while loop until the CPU cycle expired for this parent thread. Then the child thread will be scheduled and print the child, and then after child thread exit, the parent thread will be scheduled back and it recognized done flag is set to 1, therefore it will print parent end. So this is the desired output achieved by using one common variable, shared variable, done as a condition. This fix works for the desired synchronization of this problem, but the fix that we made is embarrassingly inefficient, and it wastes a lot of CPU cycles because it can busy wait, spin, wait on line number 13. By the way, don't think this problem that we're trying to solve is limited to computer science. If you happen to be in the embedded system, if you find a job as a firmware engineer, let me just write it. Firmware engineer on the embedded systems, and this embedded system firmware is designed in the spirit of concurrency. And their level of concurrency is the task level, not the thread level. Task is much smaller than the thread, and whenever the interrupt comes in, then you need to engineer the interrupt service routine. The execution of this interrupt service routine is identified as a task. When you're allowing the more than one interrupt for the embedded system, this is a plural, and so there are more than one task because each interrupt service routine is executed by a task. And this task will be computing to update the shared variable. Understanding that the complexity of writing the task in the consistent way or correct way, and the present it lecture for this recording is quite important. You need to understand how to analyze how to achieve the synchronization for the concurrent program, which you will learn from this recording. Well, let me go back to the original topic, why condition variable. Even though the fix that I presented works for the desired synchronization, but the fix presented is embarrassingly inefficient and it wastes a lot of CPU cycles. And that is the motivation of the condition variable. Instead of parent waiting on this common variable done, is any way the parent can just put itself to the explicit queue of certain condition variable, and when the child is done its job, and then signaling this condition variable so that the parent can be woken up and continue to execute. This is the use of the condition variable, and this is the reason why the pthread library supports another primitive in addition to this lock, which is condition variable. Let me show how we can use the condition variable provided from the pthread. For the pthread condition variable, you can simply Google. I just found the main page from the computerscience.kent.edu. First, you need to include pthread.h, which is obvious. And to define the condition variable using pthread, you need to tag this name of the variable with the type pthread cond_t. This specify this cond, the name cond, is the pthread condition variable. And then you can use the default initializer, like a mutex initializer. You can do the similar thing, pthread cond initializer, that will initialize this condition variable. Or if you would like to pass some other attribute, then you can specifically use this API, pthread cond init. There are two additional APIs that you need to understand for this lecture. One is pthread cond signal. Please note the argument for this pthread cond signal is the pointer to pthread cond. The second subroutine or API that you need to understand, you must understand, is pthread cond wait. This routine requires two arguments. One is pointer to the pthread cond t. The other one is the pointer to the pthread mutex t. Remember, pthread cond wait, this API requires two arguments. One is pointer to the condition variable. The other one is a pointer to the pthread mutex. Since it is quite error-prone to correctly use this pthread condition variable, so let me first present the first implementation and then show the progress that I'm going to make to correct the errors in using the pthread condition variable. So let me bring the incorrect implementation first for the desired concurrency that I try to achieve. So let me get this Windows side. And how about this? And this is incorrect implementation using the pthread cond to achieve the desired synchronization. What is a desired synchronization? And I have multiple threads, parent and child, and I would like to achieve the correct output in this ordering. First, parent begin, followed by printing child, followed by parent and end. As I said, this slide is a working version using the one shared variable done as a condition, but as I said, this implementation is embarrassingly inefficient because it includes the parent thread need to perform the busy wait on the line number 13. To correct this performance issue, and I'm going to use the condition variable which is being provided from the pthread. The first initial attempt is presented on this slide, which is not working, which is broken actually, and let me explain why this is broken. The line number 2, which has the M, this is a pthread provided mutex, and pthread mutex initializer, and I'm using the C. C is the pthread provided condition variable, which is being initialized with the pthread cond initializer. Let's look at the main. First, it will print parent. Begin. Line number 28. The parent thread creates the child thread, which is referred as a P, and this child is the actual name of the routine the child thread will execute. This part. And then line number 29 is the continuation of the P thread. As you're already aware, at line number 29, nobody knows which thread runs first. Is it child thread or parent thread? This selection is the freedom of the pthread scheduler. Let's assume that the parent thread runs first. It invokes the thl join. So what does the thl join do? This is highlighted as the yellow color. It invokes the pthread cond wait. Please recollect, there are two arguments to use this API cond wait. The first argument is the pointer to this condition variable. In our case, is a C. The second argument is the pointer to the mutex variable, which is M. The semantic of this condition wait has two things. If the thread invokes this cond wait holding this lock M, release the lock, pass as a second argument immediately before it sleeping on the condition variable C. Once it releasing the lock M, then the parent thread which invoke this pthread cond wait will enqueue itself to the explicit queue of the condition variable. So in our case, the name of the cond is a C. This C has explicit queue, and parent thread will enqueue itself to this queue and then sleeping at blocked at this point. Remember, if it happens to be the parent thread holding this lock M, and release the lock M immediately before it enqueue itself to the queue. That's the semantic of pthread cond wait. As soon as parent thread enqueue itself to this explicit queue of the condition variable, then child thread will gain the CPU and start running. So what's the child thread do? Print the child, and then invoke the thl exit, thread exit. So let's see what thread exit does. This cond signal has important semantic. The semantic is it inspects the queue of the condition variable passed as the first argument. If there is any outstanding thread waiting, sleeping on this queue, then dequeue, and place this thread into the ready queue of the CPU scheduling. For the CPU schedule, so that will have PT, okay, parent thread. After this cond signal, a return null. Now, parent thread is ready to run. So what's the returning point? Where the parent thread is need to resume its execution, still inside of this pthread cond wait subroutine. It's not returning from this cond wait yet until it regain the lock for this M, which passes as a second argument. Even though the CPU scheduled this parent thread for the CPU, and the resuming point, returning instruction from this parent thread is inside of this cond wait, and it does to regrab this lock M. When it regains the access to this lock, then that's the point of time it returning from the cond wait. Please understand that when the parent thread is ready to run for the CPU, And here is the returning address. Returning address is inside of this routine couldn't wait. In particular, it returning to the instruction in the couldn't wait to regain the log m. As soon as it regain the log m, then it returning from the couldn't wait, and then it print parent end. And return 0. So this is, we can achieve the desired synchronization, which is expected output, which is wanted output that we would like to have as a result of correct synchronization. Does it work? Well, the assumption is, in our case, in this trace or analysis, we assume that parent thread runs first. But let's say at line number right before the 29, let's assume that this time child thread runs first. What's the child thread does? After the parent begin and it print child, oh, there's a good things, and it invoke the THL exit, which is a pthread con signal. Now, when we assume the child thread runs right after the 28, when its signal, the condition variable C, this queue is empty. There's no thread is waiting on this queue. This means, since there's no one in this queue, this is simply the no op. And it return immediately. And then return null. After this one, parent thread need to run, and it invoke the THL join. So what's the THL join do? It invoke the pthread couldn't wait on C and M. So now parent thread is waiting on this queue, but there's no one can wake, signal this condition variable to wake the parent thread up. Pthread, parent thread, is waiting on this queue forever because no thread, no available thread can wake him up. So this is, again, the race as a result of this unexpected schedule of the child thread before the parent thread after line number 28, and parent thread sleeping on this queue forever. As a result, this last parent end shouldn't be able to print it. So this is the incorrect solution. Even though we tried to fix the synchronization issue using the pthread provided condition variable, incorrect use of this pthread condition variable resulting in the starvation of the parent thread waiting on this queue forever. The problem is, again, when the child thread is scheduled first before the parent thread runs the line number 29, then the child thread invoke the con signal. In signaling the condition variable C, and the queue is empty, therefore this routine is nothing but a no op. After that, the parent thread is rescheduled, and then it invoked the line number 29, which is the thread join. Inside of this thread join, it invoked couldn't wait. It waiting on this queue for this con variable C, but no thread is available to wake him up. Thus that's a problem. So how we can get rid of this starvation, this particular race? The solution is here. The revised approach introduced one shared variable done. You need to contrast the use of this done and use of this done on the bottom slide. It's the same shared variable, but this shared variable being used with this condition variable C. I want you to recollect what was the issue. The issue is this con signal being lost. Why? Because the child thread scheduled first. To guard against this lost signal, we're going to use this done variable. As I did for the left-hand side slide, to highlight how this race condition being created, let's assume that the child thread scheduled first before the parent thread executing the line number 29. So child thread, print child, so first at line number 26, the parent being printed, after child thread being created, and it print child, and invoke the THL exit. Now, the done is 1, so this value will be set to 1, and then it invoke con signal. Since the queue for the con signal is empty, so this will be the no op and return immediately. The child thread is done. Parent thread start executing from line number 29, which is the thread join. What's the thread join do? It inspects whether the flag done is equal to 0. If this is a 0, that means the child thread hasn't been run yet. Otherwise, child thread is already completed. In that case, it does not wait on this condition variable and immediately exit. So it comes back to the line number 30 and parent end. So key idea is, by using this shared variable done, and we guard against the lost signal from the child when the child thread is scheduled in opportune time. So this fixed the issue. The problem is still remain. Can you tell where the problem resides? To highlight where the problem resides, let me clear this slide. This time, let me try the different interleaving. After the child thread being created, this time let me assume the parent thread still running. So it invoked THL join. Check the done is equal to 0. That means this is a true. Parent thread is about to execute line number 21, which is con wait. But let's assume that the timer interrupt comes in right there. Who is running? Now, child thread is running at this point, and it print the child, and then invoke the THL exit, mark this done into 1, and it invoked the pthread con signal. Since the explicit queue for this condition variable is empty, the signal is lost. And child thread is done. Now this is a time for the parent thread is resume execution, where it needs to resume. Line number 21, it invoked the con wait when it rescheduled for the CPU. Now, it in-queue itself to the condition variable C right after releasing the mutex lock M. Since no one is holding this lock, so it released the lock anyway, and it in-queue itself to the condition variable C, and Q itself, and then it blocked. It slipped on this Q. But as you see, the child thread is already done. No one can wake this child thread up by signaling this C. So this is a low signal again, so it will comes into the race again. And you need to contrast the race on this left-hand side slide and the race on the right-hand side slide. This race, or this particular starvation, no thread is available to wake the parent thread up. It comes from the different reason. Where this race comes from, the timer interrupt comes in between checking, inspecting the done and invoking the con wait on the C. So guard against this inopportune timer interrupt in between, we need to make this checking the done and invoking the con wait as one critical section. For the same reason, we need to make this region of code, line number 6.8, as the critical section again. So how we can make this line number 6.8, line number 1921 as the one critical section? Critical section means how we can guarantee this execution of these blocks of code as one logical entirety. We need the locking which is the mutex variable provided from pthread. So let's finally fix the issue of these races introduced. This particular slide presents the final solution, the working solution to achieve the desired synchronization of the output. Everything is identical on this particular slide. What extra measure that we took as a fix for this problem is we introduced one mutex variable m in use of this m correctly. As I said, we would like to make this line number 7 and 8, line number 20 and 21 as the critical section. How we can enforce the critical section? We guard against this section of code using the mutex lock and mutex unlock. This is grab the lock and release the lock. Let me first make sure whether the problem presented on this slide can be fixed by guarding against this critical section with the mutex lock. As I did, everything is identical. So parent thread first print parent begin. And child thread P being created. As we did, we assume the parent thread continued to execute. It invoked thread join. It grabbed the lock because no one is holding the lock for the moment. So parent thread successfully grabbed the lock and checked the down is equal to 0. As I did for this particular example, let's assume that the timer interrupt comes in right after checking the down. So parent thread hasn't been execute this con wait yet. Since the timer interrupt comes in right there, this time the child thread is start running. Child thread first print the child at line number 13. Invoke the THL exit, which is begin from the line number 6. It tried to grab the lock, but the parent thread is holding the lock, and then it blocked right there. That means the child thread cannot acquire this lock, therefore it's blocked again on this lock. Who is running? Who is running? The parent thread is rescheduled and start executing this con wait. Please remember the semantic of this con wait. It first releases whatever lock it holding as a second argument. It releases a lock before it enqueue itself. So the lock is released, and then in this queue, the parent thread will be queued for this condition variable C. At this point, parent thread is blocked on this queue. So who is running? The child thread is being rescheduled. So where the child thread needs to resume, the child thread is inside of this mutex lock. Since the parent thread released this lock M before it enqueue itself to this condition variable. So when child thread being rescheduled, it grabs the lock, and then it returns from the mutex lock and set the down equal to 1. And then it invoked the pthread con signal. It's signaling the condition variable C. Surely this queue has the pthread. So dequeue this pthread, and this pthread will be assigned to the ready queue for CPU schedule. After this one, so there is no one knows who will be scheduled next. Parent thread is ready to execute, and child thread is about to execute line number 9, but nobody knows who will execute first. It turns out to be it doesn't matter. So let's assume that the child thread continued to execute. So what's the next statement? It unlock, release the lock, right? So now lock is available to be acquired by the other thread. After this, unlock, and child thread is done. So who is the next thread can be executed? Parent thread, right? Because it's ready to execute. So it, assuming that the CPU is assigned for this parent thread, where the parent thread need to execute. Parent thread was interrupted where? When it enqueue itself to the queue, then parent thread will be returning to this inside of conwait subroutine. In particular, the code that grab the lock again, M, those routine will be the resuming point. Once this parent thread is rescheduled and the returning address is inside of this conwait, in particular, the section of the code try to grab this lock again will be the returning point instruction. Since nobody holding this lock, so it grabs the lock and return from the conwait. And then it released the lock. That's okay. After this returning from the thread join, it print parent end. As you can see, regardless which interleading that you allow, and this implementation using this shared variable done and consignal and conwait, which being guarded with the mutual exclusion primitive lock, mutex lock, mutex unlock. This particular implementation will solve the issue of the desired synchronization of this output printing, parent followed by child followed by parent. Let me summarize. As I said, this particular solution works. The problem is the embarrassingly inefficient implementation for the desired synchronization. There it is, line number 13. This is the pure busy wait, spin wait, which is waste the CPU cycle for no reason. To address this performance inefficiency, what we did was I introduced the pthread provided one additional synchronization primitive in addition to the lock, which is condition variable. This was the first approach, but this is incorrect. It introduced a particular race when the child thread runs first. So to fix this issue, we introduced the done variable, but this approach introduced another types of race when the interleaving comes right there in between, right here between. So to fix this particular unwanted timer interrupt, we guard this section of code, and we mark this section of code as a critical section, and we use the first important primitive for the synchronization, which is lock, mutex lock, mutex unlock. And combining this mutex lock together with condition variable, together with this shared variable done, and this is the clean solution to address the issue of the performance. There's one additional note that I would like to make. In line number 19, we use if. In line number 20, we use while. For this particular problem, as a single parent and single child, and this solution doesn't matter. You can still use the if, but using the while for the pthread conwait is always recommended way to implement this locking mechanism. And I will introduce another example. In that more sophisticated example, if you happen to use the if instead of while, then this will introduce another type of race. So what's the bottom line? What's the suggested recommendation? Whenever it is possible, use while instead of if. That's a good practice. Now, I believe you guys ready, so let me introduce more real relevant problem, concurrent problem, which is referred as producer-consumer's problem. And let me highlight how we can use this condition variable properly to solve the concurrent issue of the multiple producers and multiple consumers problem in real setting. The producer-consumer problem is known as bounded buffer problem. This bounded buffer being shared by the producer and consumer. Producer produces the item and place it into the bounded buffer, and consumer consumes the item from this bounded buffer. When we write the program in serial way such that producer produces the item and consumer consume the item from this bounded buffer in serial way, and this problem can be quite easily solved. The actual challenge of this producer-consumer problem arises when we implement this problem in the writing concurrent program. In particular, I would like to implement the concurrent program to solve this bounded buffer problem, such that producer-consumer thread working on the different section of code, and the actual implementation have no assumption when the producer and consumer runs. By achieving these two requirements, I would like to implement the concurrent program that gives some illusion of simultaneity. In other words, producer, consumer runs at the same time. Since I introduced one additional synchronization primitive in concurrent program, which is condition variable. Using this condition variable, I would like to demonstrate how we can create the illusion of simultaneity. Producer, consumer runs at the same time without violating the synchronization requirement. What is the requirement? Unless there is some item produced in this bounded buffer, consumer cannot consume this item from the bounded buffer. Another requirement is when all these items filled up in this bounded buffer, producer need to wait until some item is taken off from the consumer. This synchronization requirement will be reinforced using this condition variable, which is one additional synchronization primitive which we studied in this section. The good solution that solves the issue of the producer-consumer bounded buffer problem with high concurrency can be used to solve many real-setting application problems, such as high-performing the web server. The second use case is the implementation of the pipe using this solution for the producer-consumer bounded buffer problem. So this pipe is how to implement this pipe using the good solution of the bounded buffer problem. Why this pipe is the good use case for this bounded buffer problem solution? The first command separated by this pipe is the process 1. The second one is process 2. Since we already learned about the scheduler, you cannot make any assumption which process runs first. When the second process runs first, which is WC-L, it inspects whether there is any item in the bounded buffer, which is a pipe. If there is no item available to be consumed, then the second process needs to be blocked on the emptiness of this bounded buffer. P1 will be scheduled. It produces the item and place those produced items into this bounded buffer. And this pipe will inspect the queue who is waiting on this bounded buffer and wake whoever process or thread wake up from those buffer and then schedule for the CPU. This is the exact implementation of the pipe using the solution for the producer-consumer problem. By doing that way, we can increase the concurrency amongst the P1 and P2 without assuming any timing of the scheduling. You may argue why we need to use the concurrent solution of the producer-consumer problem for the implementation of this pipe. In this simple example, you may be right, but think about it. This P1 is a long-running process and P2 is long-running process. By serialize, make the P2 wait until P1 complete, and that destroys the concurrency. That actually serialize the every program. As a result of that, the overall time to finish this P1, P2 is P1 plus P2. But by using the solution for the concurrent solution for the producer consumer, there is no need for the P2 wait until P1 complete. As long as there are some items to be consumed in the bounded buffer, there is no reason for the P2 wait until the P1 is complete. That's the outstanding motivation of writing concurrent program. There's one additional motivation to write the concurrent program. Let's say P1 produce quite an amount of items, and this amount of item cannot be fitting in the physical limit of the bounded buffer. In that case, the P2 cannot wait until the P1 complete because there is no way P1 complete because it filled up the bounded buffer. So this is another motivation of writing concurrent program. The bottom slide represents the most general form of producers and consumer problems. As you can see, there are more than one producers and there are more than one consumers, and there's a shared bounded buffer has some limited numbers of entries in this bounded buffer. These producers can independently produce the item and store it into this bounded buffer. More than one consumers can independently consume whatever items, as long as there are some items in this bounded buffer, they are free to consume. So these are the most general form of producers and consumer problem. We will tackle this problem. However, to understand what are the outstanding synchronization problem to achieve concurrencies in this general form, the best way is let's reduce the complexity of this problem to find out what are the issues, what are the synchronization problem to write concurrent program for the bounded buffer problem. So here is the reduced complexity of the shared buffer problem, bounded buffer problem. There are producers and consumers, no different, but let's limit this buffer can hold just single item. And let's further reduce the complexity by limiting the number of producers into one. We will generalize this one. For the moment, let me reduce the complexity of this problem by having single producer, multiple consumers, and one item buffer. For these simplified versions of bounded buffer problem, and bottom right-hand side slide show the broken solution. And this broken solution does not have any types of concurrent synchronization primitive operation. So without having any synchronization primitives, you can clearly tell this is wrong, right? This is broken. Now, using this broken solution, let's learn where we need to put the synchronization primitive to achieve the concurrency of the producer-consumer, these simplified versions of bounded buffer problem. Let me explain the bottom right-hand side slide code. Producer is the actual code which ran by the producer thread, and this lines of code, consumer, is the routine which will be executed by consumer thread. There's a couple of methods you need to pay attention. One is a put, the other one is get. This put is the subroutine producer thread produce the item and place in this single buffer. So as you can see, the name of the variable is a buffer, the int type. For the time being, the producer produce single integer value and place onto this shared buffer. The consumer get this value from this shared buffer using this get method, and we return whatever the value in this buffer as the return value from this get. One additional note of this sample solution is this producer produce the loops numbers of time of items, and consumer consumes this loops number of times of item consumed from this shared buffer. The physical size of this buffer is 1. Therefore, the consumer and producer need to be synchronized. For the synchronization among producer-consumer threads, the one additional variable count being introduced. This count variable simply representing whether there's an item in this buffer or not. 0 means there's no item in this buffer. 1 means there is some item in the buffer. As it is, there is no synchronization primitive being used in this example. Obviously, this solution is broken. What if you are requested to solve the synchronization issue in this particular broken solution? Where you're going to place the synchronization primitives that you learned from the previous class, even just right before we studied the parent and child synchronization, right, for the output. By using those synchronization primitives, can you fix this broken solution by placing synchronization primitives in this producer and in this consumer routine for single item producer-consumer bounded buffer problem? Can you do that? And this will be quite interesting interview question. To properly place the synchronization primitives for this producer and consumer, I would like to apply the lesson that we learned from the previous synchronization problem, which is printing parent begin, and then child thread print the child, and then the parent thread print parent end. So this is the desired output synchronization, and this was the solution that I presented. I would like to apply this synchronization primitive offered from the P thread. One is mutex, and the other one is condition variable for the solution, synchronization solution for this single buffer producer consumer problem. Let me move this slide to the right. And let me bring in the solution. Still broken, but this is exact application of synchronization primitive. As you notice, in this second version, I'm using the condition variable and mutex variable. This is, as I said, this is the exact use of the mutex M and conc C for the solution for the output synchronization. I'm applying exact same strategies for the fix of this, for the synchronization fix for this bottom broken solution. Inside of the body of the loop, producer thread try to grab the locked mutex. Why we need this mutex variable? Because this section of code is the code for the critical section. So this section of code needs to be accomplished as one single entirely. It inspects whether the buffer is full. When the value is 1 for the count, that means buffer is full. Why? Because we're only dealing with a single item buffer. This buffer can hold one value. So count 1 means buffer is full. If this is true, then producer thread need to slip on this explicit Q of the condition variable. Before it enqueue itself, it needs to release the mutex lock. If the count is not equal to 1, that means buffer is empty, so it can produce the value for I. After producing the value to this bounded buffer, it needs to signal this condition variable again. Why? In case if the consumer wait on this Q, then the producer must wait whatever consumer thread slipping on this explicit Q of the condition variable. If no one is waiting on this condition variable, then as I said, this const signal is nothing but simple no-op. So the statement from 8 to the 11 should be handled as one critical section. The critical section means this section of code needs to be executed as one single entirety, as a logical atomicity. After completing this section of critical section code, then release the mutex lock. So this is the fix for the producer. We also need to fix for the consumer side too. So let's inspect the code for the consumer as a fix. As we did for the producer thread, this section of code, starting from line number 20 up to the 23, should be executed as single entirety. For this reason, the consumer thread need to grab the lock before it enters this critical section. It inspects the count is 0. What's the count 0 means? This buffer is empty. Producer hasn't produced the item yet. If this is the case, the consumer thread needs to sleep on this explicit queue of this condition variable. Before it in queue itself, it needs to release the lock mutex. If the count is 1, that means it starts executing from the line number 22 to call the get method. After it getting the item from this buffer, then it needs to wake any thread sleeping on this condition variable queue. And basically the intention is if any producer is sleeping on this queue, then it signals this condition variable so that it can wake the producer up so that he can start producing the new item. After executing line number 20 up to 23 as single entirely, then it can release a lock. So this is the fix. There is still a tough question remain. Can you guarantee this revised fix actually achieve the correct synchronization for this producer-consumer bounded buffer problem? In our case, single producer, multiple consumers with a single item buffer. Can you guarantee this solution, revised fix, can actually solve the bounded buffer problem or not? This is really tough question. To answer that question, let's first code this one up. Let's run whether this solution, this fixed solution, have any glimpse of possibility to address the synchronization challenges of this bounded buffer problem or not.